In this tutorial, I'm going to show you how to prove trig identities. This is just like what your project covers. So I'm going to do a few of these examples since I'm not going to be here this week, so you can see exactly how to do this. So in this example, when I try to prove that the tangent of x is times the cosine of x is equal to sine x, that just means that I want to get one side to look exactly like the other by using my identities. So you want to look on that colored sheet and have that alongside with you while we're doing this. If you don't have that now, go ahead and get it. I'll wait. Just pause the video. So I want you to take a look at this very first piece because we want to try to get this to look just like sine x. Or vice versa. If you want to work on the right hand side and work your way to the left, that's okay too. It's a personal preference. So I first want to rewrite this so that I understand that this is just multiplication. This is the tangent of x times the cosine of x. Now the cosine of x is a parent function. There's nothing I can manipulate that with. It doesn't have an identity, but what I do know is that tangent x can look different. I can actually rewrite tangent x as sine x over the cosine of x. That's the tangent identity. And this is still being multiplied by the cosine of x. So this is how we're going to do these identities. We're going to use the ones that we know to prove that one of the sides, the left-hand side of this equation, is equal to the other side by manipulating the look of these trig functions. So right now this cosine of x is the cosine of x over 1, and when I multiply these two together, these cosine of x's actually cancel each other out, and all I'm left with is sine x. Now every time you get something new or something looks different, check to make sure that it matches what you're trying to prove. When I look at the very beginning, have I proved that the tangent of x times the cosine of x is equal to sine of x? And the answer is yes, because I used my manipulations to get me there. So I put a check mark next to it so I know that I'm good, and that's it. Your process as to how to get from the first step to the last step is your proof. It's not like the geometry proofs. Okay? These are algebraic proofs. So let's take a look at another example. So here's our second example, and it says prove that the sine of 2 alpha over the cosine of alpha equals 2 sine alpha. Notice where the 2's and the alphas are. This first part right here is not the same thing as 2 sine alpha. They're totally different things. This is what's called, this part right here, is called a double angle formula, because if you look at where the angle would be, I'm doubling it with that 2. So that's why they're called double angle formulas. Now, the sine of 2 alpha actually only has one identity, because this looks disgusting. There's nothing I can replace sine 2 alpha with besides that double angle identity. So I'm actually going to start on the left-hand side and try to prove to the right. So I'm going to rewrite this fraction as using the identity. So make sure that you're looking on your chart with me so that you see where all this stuff is coming from. I'm going to write sine 2 alpha as 2 sine alpha cosine alpha. If you don't understand where I saw that or why I replaced it, look on your chart where it says sine of 2 alpha and see what it equals. It should look exactly like this. Go ahead and pause the video if you need to and look. And this is all over the cosine of alpha. All right. Now, what I see here is the way that this looks right now, in the numerator, all of this is just being multiplied. So I can actually cancel out these cosine alphas. They're gone. And what I'm left with is 2 sine alpha. So, have I proved the identity? The answer is yes. So I just put a check mark. If you want, you can come up with your own way of showing me that you're done. You could box your answer in, or you could color code it, you could highlight it with a highlighter. It really doesn't matter to me, as long as it's clear that you have finished your proof. All right, let's take a look at another example. Okay, so in this example it says to prove that the cosine of 2t all over cosine t plus sine t is the same exact thing as cosine t minus sine t. Now this numerator, cosine of 2t, is another double angle identity. However, this guy has 3 different identities, so we need to look at each one of them carefully and decide which one we need to use. So on the right hand side, I went ahead and listed what the cosine of 2t is equal to. These are our 3 options, 1, 2, and 3. So which one am I supposed to use? So try to see what you're trying to cancel it out with. In the denominator of this fraction, I have a cosine t and a sine t. So, and this will take a little bit of practice until you get comfortable with these, but I'm thinking this last one will probably be the most useful because it has both cosine and sine. So maybe it will be pretty helpful. So that's what I'm going to use. And like I said, if you don't know which one to use, this is going to be a trial and error process. So don't get frustrated. You're just going to have to work them out one by one if you don't know. Or if you can't make some kind of a guess. So I'm going to erase this, and we're going to go ahead and do our substitution. Alright, so I'm going to go ahead and rewrite this as the cosine squared t and minus sine squared t all over cosine t plus sine t. All right. So let's see, how was this helpful? Because we're trying to get from here to this ending, cosine t minus sine t. So all of your rules of algebra are going to have to come into play here, and you're going to have to go back and access a lot of this in your head. I want you to take a look at the numerator right now, because as I see this, because I've practiced this many times, I notice this right here to be a difference of perfect squares. And so you're going to want to keep looking for those from here on out. So keep in mind, I can rewrite this, if this is a true difference of perfect squares, as the cosine of t plus sine t times the cosine of t minus sine t. That's difference of perfect squares. That should be familiar to you, not even from Algebra 2, but from Algebra 1 as well. And the denominator did not change, so I'm just going to rewrite it, cosine of t plus the sine of t. So I want you to see why this was helpful, because I have this piece right here and this piece right here that are the exact same, so I can cancel them out. And this is perfectly legal to do, because in the numerator this expression is being multiplied by this other one. So it is okay to cancel out those two expressions, as long as they're the exact same. So my final answer is cosine of t minus sine t. And that does look like the right-hand side of my proof, and therefore I am done. That was my proof. All right, let's take a look at a more difficult one. Okay, so this is a big one. This says to prove that the cosine of phi minus 1 all over sine phi plus the sine of phi over cosine phi plus 1 is the same exact thing as cosine phi minus 1. So we're going to see if we can condense that entire addition of those two fractions into this one itty-bitty expression, which would be pretty nice. Now, my suggestion, anytime you have fractions that are being added together, is to combine them into one fraction. And we do that by finding common denominators. However, what is the common denominator between this and this? Well, let me take you back to Algebra 2. I'm going to first rewrite this sum of fractions, so cosine phi minus 1 over sine phi plus sine phi over cosine phi plus 1. In order to add fractions, that have very, very different denominators that are not just like a number like 4 or 8 or 16, 12, something nice, is you just multiply each other's denominator by itself. So let's take a look at the left-hand side first. So I'm going to get my multiplication set up and my fraction. So I'm going to multiply this denominator, my sine phi, by the other fraction's denominator, which is cosine phi plus 1. So cosine phi plus 1, and whatever I do to the numerator, I have to do to the denominator. All right, now let's take a look at the left-hand side, or the right-hand side, I'm sorry. I'm going to multiply this guy over here by the denominator of the other fraction, which is just sine phi. So sine phi over sine phi. So I want you to just for a second look at what I'm making this denominator here, this product, and this product. If you notice, they are the exact same, and that's what a common denominator is. So this is a little bit more complex, but the idea is still the same. Okay, so I'm going to get rid of those, and let's go ahead and make our one big fraction. So I'm going to get this started over here, and right now my denominator is just the product of those two denominators, so I'm going to write that as sine phi times cosine phi plus 1. That's my denominator. And now I need to see what I can do with the new numerators. So I first of all want to direct your attention to the left-hand part up here. I want you to take a look at this product. Okay. Now, I want to remind you that I just previously, in the previous example, showed you how a difference of perfect squares breaks down. Okay. This is a difference of perfect squares broken down into factors. So if I were to multiply this out just by using my simple FOILing methods, I would come up with the cosine squared phi minus 1. Now, if you're not sure about how I got this, I want you to take this in your mind and think about how you would break it down as a difference of perfect squares. And you should be getting this expression here. Okay, this entire thing right up here. All right, now, the next part on the right-hand side is I've got two sine phis being multiplied together, which should give me sine squared phi. All right. Now, I'm going to double check. I just did a whole bunch of stuff. I'm going to see if I'm anywhere closer to getting to the right-hand side of my proof. I'm supposed to have cosine of phi minus 1. Ugh, and right now, that's not what it's looking like. In fact, I have no signs at all in that proof, and so let's try to get rid of them. So I know that I can rearrange this a little bit by doing a little bit of manipulation in the numerator here. I want you to remember your Pythagorean identity, which is this right here. And I will erase all of the identity stuff that I'm showing you in just a minute. But watch what happens here. Remember that I'm trying to get rid of sine squared phi here because it's nowhere in my proof. So I'm going to try to get sine phi all by itself. So I'm going to subtract a cosine squared phi to both sides here. And pretend that I'm doing that to the right-hand side as well. I just can't fit it over here. So these are going to cancel, and I am left with sine squared phi is equal to 1 minus the cosine squared of phi. So here's what I'm going to do. In my numerator, I am going to replace this piece right here with this piece down here, 1 minus cosine squared phi. So you can manipulate your Pythagorean identity, or any of them in that matter, to fit what you need them to work with you for. All right, so I'm going to erase this, and I'm going to replace this in the very same step with 1 minus cosine squared theta. right, so there we go. So let's see what we can do in the numerator here. I do notice that these ones are going to cancel each other out. So goodbye and goodbye. And then I've got a problem. Because what's going to happen is this cosine squared phi and this cosine squared phi are going to cancel each other out. And then all I'm left with in the numerator is 0. Oh no. So this might be a common error that you run into as well. Now, I did not intend to go down this path, so I apologize, but this is something that's very common. So I have to backtrack and try a different way to do this. So let me show you what I'm going to do. I'm going to erase all the marks here, and I'm going to go back to my... Alright, so I want to apologize for one thing. Look up here at the proof real quick. I wrote this down wrong because I'm a big dope. But the right-hand side, this cosine phi minus 1, should not be that. It should actually be 2 over sine phi. I was looking at a completely different thing, and I'm really sorry about that. This process up to this point in time is still the same. We have not done anything wrong. So I want you to look back down here at the Pythagorean identity, the one that's starred right here. And since getting this just in terms of cosine in the numerator didn't work, let's just try putting it in terms of sine. Okay, now I'm going to do this in a little bit different of a way. I'm going to actually subtract 1 from both sides first. So I'm trying, you'll see what I'm doing in just a second, if you don't right now. So that means I'm also, at the same time, I'm going to subtract sine squared phi from both sides as well. So on the right-hand side, the 1s would cancel, and all I would be left with is that negative sine squared phi, okay, because now these cancel. And on the left-hand side, I have cosine squared phi and then minus 1. So look up here at the numerator, and you see that this looks exactly like how this looks, and it is equal to negative sine squared alpha, or phi, I'm sorry. And I think I ran into yet another problem, because when I replace that part with negative sine squared phi, and I add it to sine squared phi, these are going to cancel each other out. So we're running into a few problems, and I was just looking back through my notes, and I think I might have to make a separate tutorial for this one. I think myself, I think I messed it up a little bit. So keep this on your paper, keep some space at the bottom. I will put up a different tutorial that explains how to get through this, but we're going to move on to the last one. So get ready for the next example, example number 5, and put this problem to rest for now. Okay, so here's our last example. It says prove that the sine of t over 1 minus cosine t is equal to 1 plus cosine t over sine t. Now these look pretty similar, but they're very different. Now the method that we're going to use to solve or to prove this identity is called conjugates. So while I'm doing this problem, I'm going to refresh your memory about what a conjugate is. I'm going to go ahead and rewrite this problem. And a conjugate is very simply the same exact expression, but with a different sign. So what should I do here? This is a method of getting around proving identities. So look at the denominator here, because this is the part that I don't want, and I could possibly manipulate this so that I could get something maybe a little bit different, so I could use some substitution. So my two terms are 1 and the cosine of t. Now the sign used here in black was a subtraction sign. So in order to make its conjugate, you do something very simple and you switch the sign. That's all you have to do. And we're going to do that to the same thing as the numerator, so that I do not change the integrity of the problem. And that is a method of getting through these identities. So let's go ahead and do a multiplication. So I'm just going to rewrite my numerator as sine t times 1 plus cosine t. I am not going to distribute. You can if you want to. It's not going to change anything. And my denominator, once again, looks like a difference of perfect squares. So I'm going to write that as 1 minus cosine squared t. So this looks a lot like the Pythagorean identity. So let's rewrite it and see that when I manipulate it, I need to get exactly what I'm looking for. So I'm going to go ahead and subtract cosine squared t from both sides. Okay, these cancel, and I'm left with sine squared t equals 1 minus cosine squared t. And that is exactly what I have up above. So I'm going to continue this over here. So sine of t times 1 plus the cosine of t all over sine squared t, because I replaced this expression, 1 minus cosine squared t, with this. Now, we've got a sine t here and a sine squared t here. This means right here that I have two sines being multiplied together. So I actually know that one of these are going to cancel each other out. So this one's going to go all the way away. And then here I'm just going to have 1. So my numerator is going to look like 1 plus the cosine of t all over just a plain old sine t. And if you look at what I was trying to prove, I actually made it to the finish line. So that's it. That's how we're going to prove identities. This is how you're going to do your project, and I do expect you to start working on it this week. Try to aim to get half of them done since this is due next Friday, and I will see you in the next tutorial.